we see that A inverse, which we write as the inverse of our original A matrix, is equal then to this mess here. Okay? That means that A times A inverse ought to equal the identity, and you should multiply this matrix by this matrix, multiply rows by columns, and see that we get 1s on the main diagonal and 0s every place else. So this is I do believe this is a correct matrix. We actually cheated and used derive to get this to avoid having to do all the arithmetic with these fractions. And using derive, it's real easy. You just do a to the minus 1, just like you do any other power of a matrix, and you get the inverse. And derive actually uses the whole process of matrix reduction in order to find its inverse. Does something very similar to find its powers. Okay. If we had a system or a bunch of matrix equations, AX equals B, where A is the matrix that we just saw, if we had 3 different B's, we could set this system up and reduce it. Okay, the AX equals B is going to be equivalent to this matrix. And if we reduce this to the identity, then what we have over here will be our solutions for x1, x2, and x3, or whatever we call our 3 variables. Alternatively, we could simply multiply B by the inverse of A. Okay, so here's A inverse. We multiply that by B. Now that's especially convenient if we have derive, because we could simply write, assign the matrix A, then assign the matrix A inverse. Actually, assigning the matrix A, we don't have to assign A inverse. Just once A has been assigned, A colon equals this matrix, then we can just do A inverse times whatever we want. And we obtain the solution to this equation. That is the x, y, and z that would give us these 3 numbers. So that to the equation 2x plus 3y minus 4 equals 3, 5x plus 7y plus 6z equals negative 2, 2x minus y minus 3z equals 5, we would get the solution A inverse, which is this matrix, times the 3, negative 2, 5. And the 3 numbers that we get from this multiplication will be the solutions x, y, and z. If we then want to do this one, we just replace the 3, negative 2, 5 with a negative 1, 4, 7, multiply the matrices, and we get another x, y, and z corresponding to these numbers on the right-hand side. And we can continue doing this for as many b's as we wish. As a matter of fact, we could put all the b vectors into one matrix and just multiply the inverse by the matrix consisting of all those columns. And then the columns of the resulting matrix would just be the solutions to the respective equations, to the respective systems of equations.